Take a look at these: milk, butter, gelatin, mayonnaise, muddy water, and colored glass. We use them in our day-to-day life. But have you ever wondered about the chemistry hidden in them? These substances are known as colloids in chemistry. Colloids play an important role in interface science and in the fields of energy, food, mineral processing, pharmaceuticals, and environment. Colloids are one of the three major types of mixtures, the other two being solutions and suspensions. The three kinds of mixtures are distinguished by the size of the constituent particles. You already know that solutions are homogeneous systems in which the diameter of the solute is less than 10 to the power minus 9 meters. These particles are not visible to the naked eye. Common salt in water is an example of a true solution. On the other hand, a suspension is a heterogeneous system. The particle size of the molecules in a suspension is more than 10 to the power minus 6 meters. These particles can be seen with the naked eye. Sand in water is an example of a suspension. Colloids are mixtures whose particles are larger than the particles of a solution, but smaller than the particles of a suspension. The suspended particles in a colloid are small enough to settle down due to gravity. Thus, colloids represent an important and a large group of systems intermediate between solutions and suspensions. Therefore, a colloid is a heterogeneous solution in which the particle size ranges from 10 to the power minus 9 to 10 to the power minus 6 meters. These particles are not visible to the naked eye, but can be seen under a microscope. Milk, blood, honey, and starch solution are all colloids. Colloids are also called colloidal dispersions because the colloidal particles are dispersed throughout the mixture. For a colloidal solution, we use the terms dispersed phase and dispersion medium. The phase that is scattered or present in the form of colloidal particles is called the dispersed phase, and the medium in which the colloidal particles are dispersed is called the dispersion medium. For example, in a starch solution, starch represents the dispersed phase, while water represents the dispersion medium. Colloids can be classified on the basis of the physical state of the dispersed phase and the dispersion medium, the nature of interaction between the dispersed phase and dispersion medium, the type of particles of the dispersed phase. Let us first discuss the classification based on the physical state of the dispersed phase and the dispersion medium. Depending upon the physical state of the dispersed phase and dispersion medium, 8 types of colloidal systems are possible. Dispersion of a solid, in a solid, liquid, or gas dispersion mediums result in the formation of a solid sol. fluid sol, and an aerosol respectively. Colored glass and gemstones are examples of solid sols. Paint, muddy water, and cell fluids are fluid sols. Fluid sols are mostly referred to as sols. Examples of aerosols are smoke and dust. Dispersion of a liquid in a solid, liquid, or gas dispersion mediums result in the formation of a gel, emulsion, and an aerosol respectively. Examples of gels are cheese, butter, and jellies. Milk, hair cream, and certain medicines are examples of emulsions. Fog, cloud, mist, and insecticide sprays are examples of aerosols. Dispersion of a gas in a solid or a liquid dispersion medium results in the formation of solid sol and foam respectively. Examples of a solid sol with gas molecules are pumice stone and foam rubber. While soap lather, whipped cream, shaving foam, and froth are examples of foam. It is important to note that the colloidal system of a gas into some other gas is not possible because gases always form a homogeneous solution. Since colloidal systems are heterogeneous, they cannot be obtained by dispersing a gas into another. Depending upon the nature of the dispersion media, sols are given different names. For example, if the dispersion medium is water, then the sol is called as aquasol or hydrosol. And when the dispersion medium is alcohol, it is called an alkosol. Another way of classification is based on the nature of the interaction between the dispersed phase and the dispersion medium. Depending upon the affinity of the dispersed phase for the dispersion medium, colloidal systems can be classified into two categories: lyophilic and lyophobic sols. Let us first discuss lyophilic sols. The word lyophilic means liquid-loving or solvent-loving. When substances like starch, gum, and gelatin are mixed with a suitable liquid, that is, a dispersion medium, they readily form colloidal solutions. Such colloidal solutions are called lyophilic colloids. When water is the dispersion medium, they are called hydrophilic colloids. Lyophilic sols are quite stable and cannot be easily precipitated. An important characteristic of lyophilic colloids is their reversible nature. That is, if the dispersed phase is separated from the dispersion medium, for example, by evaporation, then the sol state can be achieved again by simply mixing with the dispersion medium. Let us now discuss the second category of colloids: lyophobic colloids. The word lyophobic means liquid-hating. Lyophobic colloids cannot be formed by spontaneous dispersion in the medium, but can be prepared only by special methods. Arsenic sulfide, ferric hydroxide, gold, and other metals form lyophobic colloids. These metals are sparingly soluble, and thus their molecules do not pass readily into the colloidal state. Lyophobic colloids are also known as irreversible colloids because the residue obtained by evaporating the dispersion medium cannot be converted back into a sol through ordinary means. Lyophobic colloids are readily precipitated on adding a small amount of electrolyte by heating or by shaking vigorously, and hence are not stable. Lyophobic sols need a stabilizing agent if they are to be kept for longer times. You already know two ways of classification of colloids. Another third method of classification is based on how different substances that form a colloidal solution acquire the required particle size. Accordingly, colloidal solutions are classified into following three categories. They are multimolecular colloids, macromolecular colloids, associated colloids. Let us first study multimolecular colloids. As the name suggests, multimolecular colloids are formed when a large number of atoms or smaller molecules of the dispersed substance aggregate together to form a species whose size lies in the colloidal range. For example, a gold sol consists of particles of various sizes that are a cluster of several gold atoms. A sulfur sol consists of colloidal particles that are aggregates of S8 molecules. These molecules in the aggregate are held together by van der Waals forces. The other category of colloids is macromolecular colloids. Certain substances, like starch, proteins, and cellulose, have molecules of big size, which lie in the colloidal range. The solutions of these substances in suitable solvents are called macromolecular colloids. Synthetic macromolecules, such as polyethylene, nylon, and polystyrene, also form colloids when dispersed in suitable solvents. Macromolecular colloidal solutions are stable and resemble true solutions in some respects. Now, we will discuss the last category of colloids, namely associated colloids. There are some substances that behave as normal strong electrolytes at low concentration, but behave as colloidal solutions at a higher concentration. The colloidal behavior is due to the formation of aggregates of small particles. Such aggregated particles are called micelles, and the colloid thus formed is called an aggregated or associated colloid. Surface active agents like soaps and detergents are examples of associated colloids. The formation of micelle depends upon two factors: the concentration of the dispersed phase and the temperature. The formation of micelle takes place above a certain concentration called critical micelle concentration or CMC. And above a particular temperature known as Kraft temperature or TK. Every missile system has a specific value of critical missile concentration. For soaps, the CMC is 10 to the power minus 4 to 10 to the power minus 3 moles per liter. Each missile contains at least 100 molecules. Missiles are generally formed by specific types of molecules that have both lyophilic as well as lyophobic ends. Soaps consist of sodium or potassium salts of higher fatty acids and are represented as RCOO minus Na plus. In soaps, the alkyl group that consists of long carbon chains is lyophobic, while the polar group is lyophilic in nature. Molecules with lyophilic and lyophobic ends are called surface active molecules or surfactant molecules. Let us now discuss the mechanism of missile formation. In sodium stearate, the long hydrocarbon part of stearate radical, that is C17H35, is the lyophobic end, while COO- is the lyophilic end. When the concentration of the solution is below its CMC, sodium stearate behaves as a normal electrolyte and ionizes to give sodium and stearate ions. These stearate ions remain on the surface of water and orient themselves in such a way that the lyophilic end of the COO- dips in water, while the lyophobic part, the C17H35 part, stays away from it. At the critical missile concentration, the polar COO part is pulled into the bulk of the solution. Thus, a cluster is formed with the hydrocarbon chains pointing towards the center of the sphere, and the COO- part oriented outwards on the surface of the sphere. The aggregate thus formed has the dimensions of a colloidal particle and is known as an ionic missile. Detergents like sodium lauryl sulfate undergo missile formation in a similar manner. The cleansing action of soaps is based upon its tendency to undergo missile formation. The stearate ions of soap arrange themselves around an oil droplet in such a way that the hydrophobic part of the stearate ions is directed towards the oil and the hydrophilic part projects outside. The hydrophilic part, being polar, interacts with the water molecules, and the oil droplet is pulled away from the cloth into the water to form an ionic missile. The stearate ions of soap molecules help in making a stable emulsion of oil with water, which is later washed away with the excess of water. A sheath of negative charge is formed around the globules, which prevents them from coming together and forming aggregates. We can also say that soap acts as an emulsifier and helps an emulsion stabilize. Lyophilic salts are readily prepared by mixing the dispersed phase and the dispersion medium. However, lyophobic salts are prepared by special methods, since they have no affinity for the solvent. The methods for the preparation of lyophobic colloids can be broadly classified into two categories: condensation or aggregation methods. Dispersion methods. We will first discuss the condensation or aggregation methods. As the name suggests, in condensation methods, the smaller particles of the dispersed phase aggregate to form larger particles of colloidal dimensions. That is, the constituent particles in true solutions, such as ions or molecules, are allowed to grow in size to particles of colloidal dimensions. The colloidal solutions are obtained by certain chemical reactions, namely double decomposition, oxidation, reduction, and hydrolysis. Let us now discuss some typical reactions for the preparation of salts. Arsenic sulfide salt can be prepared by a double decomposition reaction. Hydrogen sulfide gas is passed through a dilute aqueous solution of arsenic oxide to yield arsenic sulfide salt. A colloidal solution of sulfur can be prepared by oxidizing an aqueous solution of hydrogen sulfide with an oxidizing agent like sulfur dioxide. Salts of gold, silver, and platinum can be obtained by the reduction of dilute solutions of their salts with a suitable reducing agent. For example, gold salt can be obtained by reducing a dilute aqueous solution of its salt with formaldehyde. Another reaction commonly used for the preparation of salts is the hydrolysis of the corresponding chlorides. For example, if a small quantity of ferric chloride is added to boiling water, a ferric hydroxide salt is obtained. Let us now discuss the second category, dispersion methods for the preparation of colloids. As the name suggests, in these methods, bigger particles of a substance, like a suspension, are disintegrated into particles of colloidal dimensions. The two common dispersion methods are electrical dispersion or Bredig's arc method and peptization. Let us discuss electrical dispersion or Bredig's arc method first. This method is commonly used to prepare colloidal solutions of metals such as platinum, silver, and gold. In this method, two electrodes of the metal whose colloidal solution is to be prepared are immersed in the dispersion medium and an electric arc is struck between the electrodes. The intense heat of the arc vaporizes the metal, which gets condensed immediately in the liquid to form a colloidal solution. This method thus involves dispersion as well as condensation. We will now discuss the preparation of salts by the peptization method. Peptization is defined as the process of converting a freshly prepared precipitate into colloidal form by adding a small amount of a suitable electrolyte. The electrolytes used for this purpose are called peptizing agents. This process involves the preferential adsorption of suitable ions from the electrolyte by the particles of the precipitate to form charged species. These charged species repel one another, and as a result, the precipitate disintegrates into colloidal-sized particles. It is important to note that freshly prepared precipitates are preferred because the particles are not firmly attached to each other and therefore undergo disintegration easily. For example, the addition of ferric chloride to a freshly prepared precipitate of ferric hydroxide converts it into a colloidal solution reddish-brown in color. Here, the ferric ions from ferric chloride get preferentially absorbed by the ferric hydroxide precipitate. The colloidal solutions prepared by the methods we just discussed are generally associated with some soluble impurities and some excess of electrolyte. Though a trace amount of the electrolyte is sometimes essential for the stability of the colloidal solution, an excess of it causes coagulation of the sol. That is why the sols obtained are subjected to purification to get rid of excess electrolyte. The methods commonly employed for the purification of colloidal solutions are dialysis, electrodialysis, and ultrafiltration. Let us discuss these methods one by one. The first method is dialysis. It is defined as a process to remove a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. This method is based on the fact that colloidal particles cannot pass through a parchment or a semi-permeable membrane, but the ions of the electrolyte can. The colloidal solution is taken in a bag of cellophane or parchment, which is suspended in a vessel through which fresh water flows continuously. The impurities slowly diffuse out of the bag, leaving behind a pure colloidal solution. The apparatus used for this purpose is called a dialyzer. A modified form of dialysis is known as electrodialysis. The ordinary dialysis process is a slow process. To hasten the process of purification, dialysis is carried out by applying an electric field. In this process, 2 electrodes are placed in the water compartment as shown here. When an electric field is applied across the electrodes, the ions of the electrolyte present as the impurity diffuse towards the oppositely charged electrodes at a faster rate. An important application of dialysis is in artificial kidney machines, where it is used to cleanse the blood of patients whose kidneys have failed. Let us now discuss the third method for the purification of colloids: ultrafiltration. It is important to note that colloidal particles can pass through ordinary filter paper because the pores in the filter paper are bigger than the colloidal particles. The separation of a solute from a colloidal system can be carried out by using an ultrafilter, which has smaller pores than an ordinary filter. Ultrafiltration is defined as the process of separating the colloidal particles from the solvent and the soluble solutes from the colloidal solution by specially prepared filters, which are permeable to all substances except the colloidal particles. The size of the pores in the filter paper can be decreased by soaking it in a solution of gelatin or collodion, followed by hardening with formaldehyde. Usually a collodion solution is a 4% solution of nitrocellulose in a mixture of alcohol and ether. The filter paper thus formed is known as an ultrafilter and prevents the colloidal particles from passing through it. Ultrafiltration, however, is a slow process. It can be speeded up by applying suction or pressure. To get a pure colloidal solution, the colloidal particles left on the ultrafilter paper are stirred with a fresh dispersion medium.